This is Mr. Champlin. We are going to learn about kinematic problem solving, and we are going to study different types of problems similar to the last year but a little higher level. So let's get started. Kinematics is describing motion in terms of position, velocity, acceleration, and time. There are generally two types of situations for problem solving. The objects are moving with a constant velocity, and number two, objects are moving with acceleration. For constant velocity, we basically have one formula. It's just rearranged to see the different format. Average velocity is delta s over delta t. We take a derivative if we want instantaneous velocity. And then if we want to solve for position, either in x or y axes, we could use sf, it could be xf or yf, equals si plus v delta t. Now, uniform acceleration is more commonly used. They're a little more involved. Uniform acceleration, the first equation is the definition. This is the definition of acceleration. Then you basically take this formula and rearrange it to solve for final velocity equals initial velocity plus acceleration times time. If you want to determine position, knowing initial velocity, this is initial velocity and acceleration. And if you don't know time here, you can use this fourth formula. So those are the four main formulas. In terms of acceleration due to gravity, we know that from last year that without the resistance of air friction, velocity increases by 9.8 meters per second each second. So starting at a free fall, starting at 0, it's going to be going at 9.8 meters per second after 1 second. After 2 seconds, it will double that, 19.6. After 3, it will be 29.4. So it continues to increase at this amount of velocity per each second. So one can say also it's accelerating at 9.8 meters per second squared. Now down an incline, it's a little different. Let me see if I can get this to work here. So if I have an incline, and just going to go ahead and draw this incline. Okay, so if I had a ball rolling down the incline without friction, we know gravity would act straight down. So we can break in that gravity into two components, into a perpendicular component to the incline and a parallel to incline. So we'll call this gravity, gravity perpendicular, gravity parallel. Now the component that's actually causing it to accelerate down is the component of gravity acting parallel to the incline. So if we knew this angle here, call that theta, we know this angle is a similar angle, and they're similar triangles. So basically that's G parallel. So to solve for G parallel, that's opposite. So if we know gravity, which we do, 9.8, we want to solve for G parallel, it would be the sine of theta is G parallel over G. Then just rearranging it and putting the G on the other side, you get this formula. So this is the formula you use when something is accelerating down an incline without friction. So I guess in this case the ball would be sliding down the incline. It could not roll since there's nothing grabbing the ball. Alright, we're going to do a couple example problems involving a little bit higher level kinematic problem solving than you did last year. The first one involves two vehicles. I have a Porsche acceleration of 3.5 meters per second squared is larger than the Honda's 3.0 meters per second squared acceleration. The Honda gets a 50-meter head start. Both cars start accelerating at the same instant. So we're going to go ahead and draw a kind of a motion map, in a sense, of the situation. So I'm going to have everything starting from the left side. So it goes like that. And we're going to go to the right. So the let's see, the Porsche is going to start here, and then 50 meters in front, right here is Honda. Okay, so we're gonna, and then let's see the finish line. Oh, I didn't write this in. The finish line is supposed to be 400 meters. I will add that to the question. So its finish line is 400 meters out here. Okay, so this is at 50. So we're going to go ahead and write down little initial conditions. So we'll call this S Porsche position, Porsche, I initial. And then I'm going to have T time Porsche initial. And we have velocity Porsche initial. Now we have position Honda initial, time Honda. It's not liking this. Initial. And velocity Honda. Disappearing. Every time I draw, it disappears. Let's see. Honda initial. Alright, and down here we have acceleration taking place all the way up to this point. So acceleration Porsche, acceleration Honda, and then over here we have velocity Porsche final, velocity Honda final. We have time Porsche final and time Honda final. So basically, if whoever gets to the 400 meter first will have the shorter amount of time. So if T Honda is greater than T Porsche, T Honda wins. And if T Honda is less than T Porsche, then T Honda is the winner because it took them less time. And if Porsche wins, T Porsche will be less than T Honda, assuming they're both starting at the exact same time. I'm going to write all in the givens. So we start at 0. This guy starts at a 50 meter head start. They both start at the same time. We'll call that 0, 0. They both start at rest, 0, velocity 0. Porsche is accelerating at 3.5 and Honda at 3.0. Velocity unknown. Velocity unknown. Time unknown. Time unknown. Alright, so what we don't have, a lot of times is what you don't have, you stay away from that formula. You're looking for time. You're not needing final velocity. That's not going to answer the question. It's the time. So I chose this formula. S final equals SI plus VI delta T plus 1/2 A delta T squared. Now the reason I chose that, there's a reason. I need time, so I definitely want to choose a formula with time, but I do not want to have a formula with final velocity. And if you look at this, this does not have final velocity. So this is the best formula to use. If you rearrange it, and I'm not going to show you the algebra to do this, but to solve for time, this will cancel in both terms because both are starting at rest. So that's 0. And you rearrange the formula, you end up with SF minus SI all over 1/2. Let me go down a little bit. 1/2 A square root. Alright, so I did that twice with both the vehicles, the Porsche. So plugging in the numbers, I think it would be Porsche would be 400 because of the distance, and it starts at 0, while Honda will be 450. So it would be 400 minus 0, or 1/2 A. A Porsche is 3.5. Do the same thing for Honda. Just change this to 50. You end up with T Honda as 15.1 seconds and T Porsche as 15. Let's see if we can get that out. 3 seconds. So therefore, since Honda is a smaller time than Porsche, this will arrive faster. All right. All right. We'll do one more problem here. Slide it down.